Good morning. I want to present you today a work carried out in conjunction with some colleagues of industry, Maximiliano Ancharek and Pablo Marigliani from Galileo Technologies, Argentina, and from Academy, Georg Mensa from ETH Zurich, and Laura Prieto and myself, Camilo Silva from Technical University of Munich. The idea of the work is to show you that by using high-order adjoint-based perturbation theory, it is possible to compute what seems to be very complex and expensive parametric thermoacoustic maps in a very efficient manner. Combustion stability is of great concern during the design of gas turbines, and it would be interesting, it would be desirable to know beforehand from early stages of design whether the combustion chamber is actually or is prone to be unstable or not. But this is pretty hard because we need quite a good amount of information, of data. For example, even assuming that we have already somehow fixed the geometry and the mean flow field conditions of the combustion chamber, we need still the acoustic flame response, and this is at early stages of design actually unknown. How to proceed then? Actually, an idea could be to consider a different collection of flame responses, each flame response qualitatively different from the other, and in each flame response you have a given amount of parameters with certain defined range. And the idea would be to just consider each of these values in the flame response to compute an eigenvalue problem. So remember, we just assume that geometry and boundary conditions, they remain fixed, so we assume they don't change anymore, and we just consider the flame dynamics for a given set of parameters, compute the eigenvalue problem, and we obtain the eigenmode and the eigenfrequency in terms of the frequency of oscillation and the corresponding growth rate. So after solving the eigenvalue problem, we obtain this eigenfrequency that can be represented in the complex plane, as we see here by this dot. And this is everything at a nominal point, with an example of a flame response given by a gain and a time delay. Now assume we just want to perturb the gain and the time delay, then we expect perturbations also, shifts in the eigenfrequency. So we can see here that small perturbations lead to small changes in the eigenfrequency, and large perturbations lead to large changes in the eigenfrequency. Now, as we just saw, so we have to compute each point of this complex plane is the solution of an eigenvalue problem. And this is actually pretty expensive. We cannot do that hundreds of times. That would be very, very unaffordable. So what is the idea? We will just consider an adjoint surrogate model. So we have the same input and we will have an output which we assume, or which we hope that is going to be actually very similar to the truth. The truth here considered to be the output of the eigenvalue solver. So the main question now is, what if we use adjoint perturbation theory to derive that surrogate model? So this is the outline. We will start with a very simple example explaining what is adjoint perturbation theory. Then we go to high order adjoint perturbation theory. And finally, we end up with results. So to explain adjoint perturbation theory, a good idea is to just go and use the first order adjoint formulation. So what does it mean? We just have a perturbation. So remember that we had represented here the flame, but it could be any other parameter in a more general sense, and we obtain the eigenfrequency, the nominal point, plus the perturbation that is originating from this perturbation of delta theta eta. And the adjoint surrogate model is just this very simple equation. You have the nominal plus a corresponding, you can consider like a sensitivity. Additionally, we observe we need the direct and the adjoint eigenmodes at the reference condition to obtain the surrogate model. Let's just dip a bit in some mathematics, some linear algebra. So we have the definition of the direct eigenvalue problem. So this is the operator L that represents the system with the flame and so on. And we have also a corresponding adjoint eigenvalue problem. You will see that here these are actually the right eigenvectors of the operator, and these are actually the left eigenvectors. And based on this, because this is all considering the nominal point, so this knot is to represent the nominal point, we want to estimate a new eigenvalue problem where each term in this eigenvalue formulation is perturbed by delta eta. So this is the input, remember, the perturbation. And then we express this as first order expansions. Here this is going to be a first order Taylor expansion. And what do we do now? We just put them, so this definition, in here. And we remember that this is the quantity we want to evaluate. After combining the previous relations, we obtain this expression. We want to have this, remember? But right now, this is kind of not possible. Then we add a very key step, a very important step, which is to project this equation onto the adjoint eigenvector here. So this is the representation of the inner product. And now, if we remember the definition of the adjoint eigenvalue problem, we can make this term vanish. And the estimation for omega 1 reads like this. Remember that the adjoint surrogate model is just a first order expansion, in this case the first order adjoint perturbation theory, and we just need this so-called sensitivity, and that's all. So what do we obtain? We see that for small perturbations in the gain and in the time delay, this first order adjoint approximation, which is represented here by the dashed lines, work pretty well, but for large perturbations it does not work very well. Here we have actually a non-monotonic trajectory in the complex plane. Well, the answer now is then, if a first order adjoint perturbation theory fails, maybe we can just consider a high order adjoint perturbation expansion. So all this theory is based on the thesis of Georg Mensa and his work recently shown in the Journal of Sound and Vibration 2020. So what is the idea now? Instead of having this first order expansion, as I showed you before, we will consider many terms in the expansion. So to give you an idea, in this work we have 16 terms. But the idea remains the same. So we have the direct and the adjoint eigenmodes that are used to build these coefficients omega 1, omega 2, omega n. So all this expression can be just represented by a sum. And these are then the quantities of interest. And now we have the same thing as before. So we have the direct and the adjoint eigenvalue problem and the solution, so the definition of the eigenvalue problem, the new one after the perturbation has been applied. And this operator, the eigenvector and the eigenvalue, now they are expressed as a power series. Before we just have a first order power series, now we have an n order power series. And here we have also a high order Taylor expansion. But the procedure remains similar. We just put all these three quantities inside the definition of the eigenvalue problem. And this is what is obtained. You can see in the thesis of Georg that all the complexity is actually immersed in this coefficient Rk. The nice thing of this Rk is that it's actually recursively calculated. So you need R2 to compute R3, then you just from this R3 you can compute R4 and so on. In this case, as I told you, we use a 16 order adjoint expansion, then we have k equal to 16. The next step is to project this expression into the adjoint eigenvector. So this is the same as before, as the first order adjoint example. This quantity vanishes, and therefore we just can reorganize this expression for each coefficient omega k. And this is what is obtained. And remember that the adjoint surrogate model therefore is going to be just written in such a way. So now we have the coefficients which are actually given this power series formulation. So we will show in the results section that this kind of approach can actually recover pretty well this kind of non-monotonic trajectories. So after using the 16 adjoint perturbation approach, we're able to have very large perturbations in the flame response, in the gain and time delay, and recover this kind of loci in the complex plane. Well, let's go now to the section results. We show here a schematic representation of a combustion chamber recently developed by Galileo technologies in Argentina. This belongs to a nanogas turbine. We use the Helmholtz solver called Pade, developed also in the thesis of Georg Mensa. We account for a three-dimensional geometry and discretize the Helmholtz equation by means of finite elements. The mean flow information is coming from runs. So let's focus now on the flame response. Remember that we consider the flame response here to be eta, and one particularity of the study we are developing, is that the unperturbed state, so the baseline condition, does not contain any flame response. So what does it mean? It means that we are actually taking into account the adjoint and the direct eigenmodes from the case without flame. So basically the acoustic modes of the chambers. We have here a passive flame. Now if we take this into consideration, we see that omega is just the sum of the nominal eigenfrequencies, so the eigenfrequencies of the system without any flame activity, plus the corresponding terms due to the influence of the active flame. The flame model can be any kind of model that can be parametrized. So for example, we can consider this the classical end-to-end model. Here we have the interaction index and the time delay. We can consider also a distributed time lag model, like the one that comes from the finite input response. You can see it in here. Or also this model that is accounts for the Gaussian distribution of the time delays and can be expressed, for example, in such a way. Something that is of interest or that is important to highlight is that the coefficients omega, they are computed completely independently from the flame response. So you can compute it once, and then you can evaluate this flame response, then you can evaluate this flame response, and the coefficients omega, they remain the same. Another novelty of this work is that we propose to use a univariate adjoint perturbation theory, so because we have just this eta as the flame response, but the flame response actually is accounting for many variables. In this case, for example, of a distributed time lag for the finite input response, we could have perfectly 16 values for n. But the idea is, since we have this mapping, we can actually somehow compress the information from these 16 coefficients in this example to just one complex number. So let's summarize the steps. We have first to compute by the Helmholtz solver the nominal values for the eigenfrequency, the direct eigenmode, the adjoint eigenmode. Then we use adjoint-based perturbation theory to compute the coefficients omega n. Then we will solve an algebraic equation. In this case, we use Newton-Raphson to have this mapping from 16 coefficients to one complex number. And finally, we just have to estimate the corresponding shift in the eigenfrequency given values of eta, which are actually the flame response. Okay, so let's continue with the results. We will just talk first about the power series estimation. So as said before, we start with the baseline point. We just calculate 1 times this eigenvalue problem to obtain omega naught, p naught, and the adjoint p naught. Subsequently, we use adjoint perturbation theory to calculate the coefficients omega n. Remember that these quantities are obtained from the case without flame, so basically they are the acoustic modes of the combustion chamber. And subsequently, we just introduce here in this power series the flame response. This is a complex number, remember. And we can obtain this kind of parametric map. So if we use the flame response based on the Anton model, we can just consider, or this is explained in the following. When we increase the interaction index, we get farther and farther from the baseline point in these directions when increasing and from 0 to a given value of the interaction index. Now, when we change the time delay, in this case from 0 to the first period of the acoustic mode, we see that these trajectories then will be shifted like in this counterclockwise direction. So in this case, we'll see from here until there. One question that we can ask is, can we actually trust these results? Well, this is actually given by the radius of convergence. So this given in this delta, you see that this is just an asymptotic expression. So from the coefficients of the power expansion, we will be able to obtain the radius of convergence. And if we plotted this in the complex plane, we will see that everything that is inside can be considered accurate. Everything that is outside maybe shouldn't be trusted. Now, a side note while passing, it's interesting to note that this borderline of this convergence is given by the exceptional points. So these exceptional points are like singularities in the omega space. So if we didn't have any exceptional point at all, so we could have this power series being accurate over a very large range. Now, the existence of these exceptional points actually limit the radius of convergence of power series. This interplay between exceptional points, thermoacoustics, and high-order adjoint perturbation theory has been actually recently studied by this paper of Alessandro Orchini, recently published in the Journal of Fluid Mechanics in 2020. Now that we have the radius of convergence, we want to know if all these calculations make some sense. Then we actually had to solve for every single point a Helmholtz solver for validation purposes. We see that there is a very good agreement between the power series and the Helmholtz solver within this radius of convergence. As expected, also outside, the accuracy of the power series actually is lost. But now we may ask, what can be actually done to increase the validity range of the surrogate model, here proposed by power series and adjoint-based perturbation theory? Well, let's take a look at the Pade approximant. So we just saw that the power series, the radius of convergence, is limited by singularities in omega. This can be actually understood. The power series is based on a polynomial and therefore does not have any singularities. It's an entire function. I cannot characterize with a high fidelity, let's say, what the omega function is telling us, which actually has singularities and therefore can be seen as a meromorphic function. But what happens if we just convert this power series into this rational function, which is given by a Pade approximant? We will see that this Pade approximant is not limited by singularities in omega. And this mapping between the coefficients of the power series to the coefficients of this rational function, which is the Pade approximant, is actually straightforward. You just need to know the coefficients omega k and then solve a linear system to obtain the coefficients AL and BM. And this is like magic actually, because you can see that the Pade approximant, now represented by these crosses, actually it has also good accuracy even away or be even outside the radius of convergence of the power series. So we have seen that by means of Pade approximant, we are not strictly limited by the radius of convergence of the power series, and we are not limited by the existence of exceptional points in the vicinity. And this slide can be of high interest for industry. We can see that we use only a fraction of what it had to be used when using the Helmholtz solver calculations. So, how this is computed? We just know that for this case we have 357 points. Then we multiply this by the time that the Helmholtz solver requires. So in this case we have 30,000 seconds more or less. Now for the perturbation theory, we just need to compute this once. Then we just apply the perturbation theory to obtain the coefficients omega k, to do this mapping from power series to Pade approximant, for example. And all this is obtained only in 108 seconds. Now we do the ratio 108 over 30,000. We observe that we are actually increasing the efficiency more than 100 times. This slide is of interest because we want to show that is it possible to use flame responses that are not simplistic end-to-end models. We can just consider another flame response and consider another parametric map, but just take into account that we didn't have to compute again the coefficients omega. So perturbation theory was already applied, and now we are just solving the surrogate model. Now we are in the last slide. So the takeaway ideas. We use high order adjoint perturbation theory to show that we can have accurate thermoacoustic maps in a very affordable computational manner. These kind of thermoacoustic maps, in the case when they are obtained from flame response models, can be actually very useful in the early stages of design in combustion chambers. So what does it mean? That we can compute the drift of the eigenfrequency caused by flame dynamics with negligible additional computational costs. We have the surrogate model that needs the direct and the adjoint eigenmodes as ingredients to compute the coefficients omega n. And then from there we can just use any flame response we want to consider this shift in the eigenfrequency, so the new eigenfrequency. We can use, for example, the end-to-end model. We can use distributed time lag models without needing to compute again the coefficient. This is just done only once. Well, so thank you very much for your attention, and I will be happy to answer any questions you may have.